Arratsaldeon eta ongi etorriak guztiak Passion for Knowledge jaialdiren 3. jardunaldi honetara. Gaurko ekitaldiari hasiera emateko Dudley Hershback irakaslearen hitzaldia daukagu. Hershback irakaslearen aurkezpena egitea ohore bada. Hain pertsona ikaragarria aurrean izan da. Baina bestalde oso erraza gertatuko zait. Zientziarekin eta kimikarekin egiten duena hau da. Hain gertukoak eta divertigarriak bihurtzea, horiek baitira bere izakearen ezaugarri nagusiak. Bere biografiaren laburpentxo azkarra egingo du jarraian. Nacido en San José, California, en 1932, estudió en la Universidad de Stanford, donde se graduó en 1954 y 1955, respectivamente, en matemáticas y química. Posteriormente, se doctoró en química en la Universidad de Harvard en 1958 e inició su tarea docente en fisicoquímica en la Universidad de Berkeley. Y es aquí donde inicia sus estudios de haces moleculares de reacciones químicas elementales. La creación en 1959 de un aparato con el cual dos haces, cada uno de ellos formado por partículas de una misma sustancia, podían entrecruzarse, permitió la colisión de átomos y moléculas de diferentes especies reaccionando entre sí. Esta colisión permitió observar cómo el producto resultante escapa del lugar en el que se cruzan los haces. Con el uso de una variedad de detectores de partículas se puede determinar la energía de los productos de la reacción y la forma en que esta energía se distribuye entre las diferentes formas posibles, como la traslación, movimiento de la molécula en su conjunto, la vibración, oscilaciones internas de las partes de las moléculas y la rotación. Este nuevo campo se desarrolló rápidamente y el profesor Hershback retornó en 1963 a Harvard como profesor de química. Junto a John T. Lee, que se unió al grupo en 1967 en la Universidad de Harvard en el estudio de las reacciones químicas entre los átomos de hidrógeno y las moléculas alcalinas diatómicas, fue uno de los primeros científicos en adoptar la técnica de los haces moleculares con fines de investigación química. En 1986 fue galardonado, junto con su colaborador John T. Lee y el químico canadiense John Polanyi, con el Premio Nobel de Química por el desarrollo de la dinámica de procesos químicos elementales. En la actualidad, desde 2005, es profesor de física a tiempo parcial en la Universidad de Texas. Pero además de ser un gran científico, Hershback es un ferviente partidario de la educación científica y de la ciencia entre el público general. Suele dar charlas a estudiantes de todas las edades, transmitiéndoles su entusiasmo desbordante por la ciencia y por el descubrimiento. Como él mismo ha dicho en otra ocasión, me gusta decir que la ciencia es necesariamente un juego de niños. Una ventaja que tienen los niños sobre los adultos es que a ellos no les preocupa acertar siempre. Lo que hacen es jugar y experimentar. Y eso es algo muy parecido a lo que hacemos en investigación científica. Hay que jugar, hay que adivinar y te encuentras con que muchas veces tu apuesta no te lleva a resultados razonables, pero no pasa nada. Lo intentas otra vez. Así va la cosa. La ciencia es necesariamente un juego de niños. Pero no solo es la pasión por la ciencia, sino cómo sentirla y hacerla sentir próxima al público en general. La educación científica no debe cerrarse únicamente a las asignaturas propiamente de ciencias. Debemos tener una visión más amplia. Como el profesor Hershback también dijo en otra ocasión, la ciencia puede estar relacionada con el arte, la música. Mucho de lo que hacemos, digamos, por ejemplo, en síntesis química, donde tenemos elementos simples y enlaces químicos, por ejemplo, a menudo estamos interesados en aspectos biológicos donde los principales átomos son el carbono, hidrógeno, nitrógeno y oxígeno, los 4 básicos, y tal vez alguno más aquí y allá. Es decir, estamos hablando de elementos simples. Bien, los elementos de una composición de Beethoven son bastante básicos. No hay más que unas pocas notas, intervalos y así sucesivamente. La cuestión está en cómo los combinas. Así es que estamos hablando de lo mismo. Y ya para terminar, no podíamos olvidar otro éxito relevante del profesor Hershback. También ha prestado su voz e imagen para el capítulo de Los Simpson, Treehouse of Horror, donde se le veía presentando el Premio Nobel de Física al profesor Frink. Well, Professor Hershback, it's your turn now to explain us how to domesticate the molecules.
Thank you for that gracious and lovely introduction. I think you improved some of the quotations from me very much. In any case, I'm delighted that you emphasized art and music, because I think science has a great deal in common with those things. What we celebrate in those fields is the opening of new perspectives, say in architecture. And that's, of course, what scientists try to do. You heard yesterday, many of you, from Jean-Marie Lane, a beautiful lecture. He called it, he said to me, a sermon about chemistry. He went in the direction of complexity. I want to go, as you have pointed out, in the direction of simplicity. But as Pedro has mentioned, quoting a famous remark by Einstein, you should try to make things as simple as possible, but not more so. I'm delighted, like I think everyone who's had a chance to take part in this, to be here at the passion for knowledge, and to have, again, the opportunity to congratulate the DIPC for its remarkable growth and development over 10 years only, so still a youngster. And of course it reflects the extraordinary leadership of Super Pedro, as we call him, and his super staff of people. And I want especially to point out my appreciation right away for the slides you're going to get to see. They are all artistic, but not because of me, because Pedro was so disgusted with slides I had personally made, not for this occasion, but another one, that he commissioned an artist scientist. I think he's right there. Gonzo Alvarez, wave your hand. And so he is responsible for these slides. They are so nice that I may have difficulty talking because I'll be looking at them in admiration. But it means that you can do likewise and won't have to listen to me that much. In order to be sure I can finish in time, I've written out the speech, but I'm not going to read it all, naturally, just to be sure I could, in principle, get through it. We have a technical problem here. The essence of my talk is about the motion of molecules and reactions, and it looks as if maybe you sped up this, made this slide more artistic than I expected. But I'll just, maybe while the expert comes and sees if we can tame it down a little, I'll give you my first paragraph. See, the trouble with writing a draft beforehand is you got these words you struggle to get just right, and then you have to ignore them to deliver the talk right. So I say, which agrees with many people, including Jean-Marie Lane, the essence of chemistry is transforming one substance into another. And often these transformations seem almost miraculous or magical. I became intrigued with that question. How do the molecules accomplish this gymnastics and shifting atoms around between them in a reaction? And I really first became intrigued with it even in high school. And not many years later, it became a passion that continued for decades. It's still with me. And that happened, the passion arose when I recognized that it might be possible, at least for some elementary reactions, just involving an atom and a small molecule, to develop methods to actually resolve the molecular gymnastics that occur in a chemical reaction, in a single reactive collision. Let's see if we can move up one step. Well, I guess he's working on it. And this indeed has worked out because so many very able people joined in this quest, which we pursued with passion. And it has provided tools that do indeed allow you to resolve a lot learn a lot about how the molecular motions and forces govern the reaction in single collisions between pairs of molecules. That has become a major field of physical chemistry. It's now called reaction dynamics. Now, I intended to show you the next beautiful slide. I wonder if I can lift up this and just press the button. Let's try it.
We'll take a short break.
Oh, we're going to have to take a short break?
Yeah, I think we'll take a
Oh, shucks. That's too bad.
Yeah.
You won't let me keep on going and entertain people during the short break?
Well, you want to use your images.
Well, you have to make it. That's all right. I don't need the image. I want to start with a story.
It's the magnetic power of Dudley Hershback.
Well, who knows? Maybe you shouldn't watch that one too much. You're going to get dizzy. But I wanted to
Vamos a dejar que lo resuelvan para que Dudley pueda dar la charla como él quiere darla.
I can show this other slide afterwards. So the first one's so beautiful, people maybe want to watch only it. But soon after I arrived in college, which was quite a while ago, 1950, I brashly asked my freshman advisor, Professor Harold Johnston, thank you, what research... Yeah, we'll leave it open. Fine. Yeah, the secret is openness, he said. Open your computer. Open everything. That's a good motto. So I brashly asked my freshman advisor about his research. I had never heard of research before. I was a farm boy. I didn't know that professors did something called research. But he described his studies of chemical reactions and explained the difficulty in unraveling how they took place. The basic problem was that chemical reactions ordinarily occur within great mobs, huge numbers, enormous crowds you can't imagine even at soccer championships and so on. They're wildly interacting molecules, and chemists had to proceed by postulating a list of steps by which some molecule begats another one, which then begats one or two more, and that just keeps going on. The terrible proliferation obscuring what could happen. And Johnston emphasized this is always a guessing game. There's no way to test such schemes definitively back then. You couldn't be sure you'd included all the steps. The most interesting species usually were ones that were reactive intermediates. They were so reactive as soon as they were born, when one reaction they reacted with another one and disappeared, so you couldn't detect their presence by the methods available then. So I was quite impressed that chemists bravely, maybe recklessly, patiently tried to work out reaction steps in such situation. But only 4 years later, an offhand remark by a physics professor gave me the insight how you could resolve individual reaction steps and intermediate species in chemical reactions. The professor mentioned an experiment in the 1920s done by Otto Stern to measure the distribution of molecular speeds. He had a very simple apparatus. It was a glass tube about 25 centimeters long. He had a filament from which he evaporated silver atoms. They traveled on a rotating platform so that he could deposit silver atoms on a glass plate, but where they landed, because the platform was rotating after going through some slits, depending on how fast they were going. You see, he had no way to measure their velocity. His detector was so crude, it was just collecting the actual atoms, but by rotating, he could spread out the velocity. And by switching the direction of rotation, he could spread it the other way and double his magnitude. He only did it, his rotation, at 15 meters per second, and the molecules were traveling 600 meters per second. But it was such that he actually could get quantitative information for the first time, testing the distribution of molecular speeds that had been predicted by Maxwell and Boltzmann. So that's what intrigued me. And since we missed slide 2, let me back up and see that. Oh, sorry, go forward rather. I hope. Forward. Yeah. This is the large, except for that little box, which hopefully will go away. The large philosophical picture, historical perspective for the 20th century that I wanted you to see, that, of course, I didn't think of in high school, I didn't think of in college, but later. So what it shows down here, if I can, no, go away, please. It's labeled on the near the bottom of the mountain, thermodynamics, this famous subject. I think you just click it. Okay, thank you. Whoops, well, you're going too far, too fast. Inherited from work in the 19th century, there the pure thermodynamist was proud of the fact they did not have to, in fact, it was regarded as a bad thing to postulate anything about the molecular atomic structure of what you dealt with. You want to deal only with macroscopic observables, pressure, volume, temperature, and so on. But that's the foundation. And then came the era where molecular structure became accessible through all sorts of methods. Of course, you all know how important X-rays are, ultimately. The structure of DNA, sort of the great pinnacle of success. Before that, Pauling predicted the alpha helix structure for proteins, so on. So that was a great era. The dynamics era began, they all overlap some in here, but we still have a long way to go around this era. In particular, there was no way to observe what happened in individual reactive molecular collisions because, as I said, reactions occurred in these great mobs. But now I mentioned Otto Stern's experiment. I immediately went back to Professor Johnson, my advisor, and described with enthusiasm how I thought that's the way you could do things, across two beams. And he laughed and said, well, sure, but there's not enough intensity. And in fact, that did look difficult. Molecular beam methods had found many applications in physics, but very little had been done studying molecular collisions because it did require means to detect products at extremely low levels. For instance, in the work we undertook at Berkeley in 1960, the yield of product for a special family of reactions that was particularly favorable would correspond to a monolayer of product molecules a month. Monolayer a month. Now, to chemists, that's absurd. We couldn't run the experiment without the vacuum system we had breaking down and so on, much earlier than a month and so forth. But it turned out, naturally, or I might not be here, talking certainly on this subject, to do things in such a way that we could study those reactions in considerable detail and ultimately many others with far smaller yields. But first I'll give more background. After our first, it comes later. After our first crude experiments at Berkeley, I thought you'd enjoy this. I was asked to give a seminar in the physics department. The first time I got to talk about these, because the chemists, of course, thought this was ridiculous. They weren't much interested in it at that point. I began, of course, by praising the legacy of Otto Stern and writing his name on the backboard. Surprising to me, some professors right about there leaned together and were giggling at each other. I didn't understand until afterwards one of them asked, did you know Otto Stern was in the audience? This is 40 years after that experiment that got me so excited and decided me to pursue this course. Sure enough, I had noticed a little guy all by himself over there, dressed in black with a Homburg cat. He looked a little like Charlie Chaplin. And later I got to meet him and learn from him some stories which I have passed on as a sacred privilege, having heard them directly from Otto Stern many times. I'm going to retell just one dealing with the experiment. I've already mentioned some details about it, but he found that his data showed a systematic deviation from the theoretical result. So he did what we do now. You send out preliminary manuscripts to some colleagues. One of them wrote back and pointed out that he needed a factor he had left out in making the comparison between the theoretical prediction of the speed distribution and his data. That factor is one you can easily understand. Some of you may feel like leaving as fast as you can here out the exit. And if you were to do so for any reason, the faster ones would get there first. So that you have to put in a factor of velocity when you are selecting flux, and rather than number density. So that, Stern said with glee, that letter with that correction, which improved the agreement, came from Albert Einstein. It was only later that I learned that Stern was, in fact, although he'd got his PhD in chemistry, Einstein's first postdoctoral fellow. He joined Einstein in Prague, where he was temporarily, in 1912. So there they are. So I'll leave them on for a while because both are heroes of the tale. Now, I must emphasize how tiny molecules are and how wildly they do bang around in typical circumstances. To repeat a favorite comparison, if you take a teaspoon of water, I don't happen to have a teaspoon, but a teaspoon of water, and we're able to count the number of water molecules in it, it would turn out to be about the same number, roughly, as the number of teaspoons of water in all the world's oceans. So Sylvia talked brilliantly about our oceans. That's something you might want to mention sometime. You know, just one teaspoon of water. So another is a favorite comparison. If you imagine a hypothetical, very slow bug crawling across your thumbnail, so slow it took a year to do it, it would cross a molecule about every second. So that if you have a good feeling, I don't know if that, how quick the seconds go by, that's it. Now, another aspect, of course, small as they are, they're ripping around the air molecules, for example, in this room, with the speed of rifle bullets, crazily bouncing. At this density, they don't get to travel more than 1/10 of a millimeter before they bang into another molecule. So you see what the basic trouble is if you want to find out what really happens. This chaotic lifestyle obscures what really happens when you're making and breaking bonds in those equations that do lead to reaction. So this figure is inspired, as you might guess, by a cartoonist who heard a talk I gave in Canada. I don't know that you do a lot of hockey around here. I see Pedro nodding. You do hockey? Maybe you do everything. You're really super. I see. Okay. Well, I wish that we could generate beams with the nice properties that these hockey players have. They're just perfectly oriented in single file. And look, he added blindfolds because he thought that the molecules wouldn't be able to see one another. Well, of course, they see one another through the forces that Jean-Marie was talking about yesterday, the long-range interactions. Not necessarily, in fact, definitely not enough to produce chemical bonds as such, but other forces that, as Jean-Marie emphasized, are very important in higher range orientation. But in the molecular beam case, if we were to expand the scale so that the molecules were the size of the hockey players, they would be about 30 meters apart, not right behind each other. Furthermore, the beams would be about 30 kilometers wide. I mean, they're very small in our lab, but I'm expanding them now so the molecules now are the size of the hockey players, you see. So a tenth of a millimeter wide beam gets blown up to kilometers. So, of course, with such fleet beams, most will miss, right? In fact, when I told Kistakowski, the great experimental physical chemist at Harvard, that I got this offer from Berkeley and I was going to pursue molecular beams, he said, "Oh, too bad. You have been bitten by the molecular beam bug. The trouble with the molecular beams, there's no collisions in one beam, so there's no collisions in the second beam, so there's no collisions when you cross the two beams." That's fortunately only true in first approximation, but when they do collide, you can, of course, have something like what happens in hockey, except in chemical reactions, it's much more violent. The molecular players are going to exchange an arm, a leg, a torso, because that's what a chemical reaction is. So this is mild compared to what actually happens in a reaction. So, but it gives you some notion of what is really like. Now, the course of time, taking advantage of many other methods we could use to augment the primitive cross-beam business, we were able to resolve, even orient, not as well as this, but orient the collision partners, measure as products separated not only their velocity and preferred direction, and its distributions, but how fast they were rotating, and as you mentioned in your introduction, even how fast the atoms within there are vibrating. All that's information that gave us a lot, told us a lot about the forces that govern the reaction. Now, the early cross-beam experiments, as I already alluded to, are of necessity limited to a special family that was particularly favorable. They had very large reaction cross-sections that could be measured by means of a very simple, very specific detector. I want to emphasize how simple it was. It was just a hot wire, a tungsten filament. In fact, it had been used by Otto Stern in his lab, together with a second filament, a platinum wire, actually an alloy, that for mysterious reasons that had been empirically discovered, didn't respond to an alkali halide molecule, whereas the tungsten filament responded both to alkali atoms that were scattered without reaction and with a product, the alkali halide, formed if you were reacting the alkali with a halogen, is typically what we did. So I'll come back to that detector later. You'll see how simple it was. But this detector would produce ions for these species I mentioned, and not if you had some, as we did, pump oil and other things floating around in our imperfect vacuum, because the alkali species give up their electrons readily to a hot metal. Great surface chemistry, known by Langmuir, for example. So the fact that the detector was so simple and so specific was a great aid in the early experiments. Now, these special reactions that were so valuable in the early beam experiments went back also to the 1920s. They were studied by a still more primitive apparatus, that I love to mention, is Michael Polanyi's so-called diffusion flames. He had just a tube about a meter long. He would have argon in it at sort of half atmosphere pressure. He would diffuse sodium in one end, chlorine in the other. So there's the concentration of sodium going down as they diffuse in, concentration of chlorine. And you can see where the joint concentration was greatest. So you had the product of sodium concentration times chlorine. You got a salt deposit, sodium chloride. And because even in the 1920s, it had a pretty good idea of what the diffusion rate was, the width of the salt deposit allowed him to deduce the rate of the chemical reaction. He only, of course, measuring the overall rate of reaction, the yield, He couldn't observe any of these other details because of the collisions I mentioned. But I will note that he also saw a yellow emission, the familiar sodium D line from street lamps of sodium, PU2, and that caused tremendous discussion back in the 20s. It was very hard for them to understand it. People like Wigner, Einstein, and so on wrestled with how to explain it. And in fact, later in the beam experiments that we were able to carry out, many reactions, including that series of steps that led to that emission, were completely resolved very happily. But meanwhile, this acted as kind of a beacon, I would say, to light the way for the young chemists who wanted to pursue molecular beam reactions, because Polanyi had used various reactants and found a variation in chemical reactivity with the molecular structure. It was the first such data ever obtained. And so we hope to find in the single collision experiments that kind of evidence for variations in the dynamics of the single collision. So let's see. Whoops, I want to go the other direction. Here is a picture of Michael Polanyi, and this was taken in 1931. And here he is with his young son, John Polanyi, who plays a major role in the saga of study of single collision molecular reactions, as you'll hear a little more about later. So I will go on to show you the rather simple apparatus that was sufficient to study alkali atom reactions with halogen-containing molecules. We called it fondly Big Bertha. And it really consisted of an oven designed so you could have molten alkali, lithium through cesium, any of those elements, sodium, potassium, rubidium, heat it separately so that the temperature here wouldn't be tied to the melting business, but act more like a permanent gas, so it wouldn't be so sensitive to temperature fluctuation. This was about 6 centimeters long. The beam of, in our first reaction, methyl iodide was about 1.5 centimeters. This is in scale. And this was about 8 centimeters to the surface ionization detector that I've already described. So you see, it was a pretty simple thing. We had a rotating lid, so with graduate student Volga Boatsong, you could just rotate the lid to scan the distribution angle of the elastically scattered alkali and the product. In this case, I mentioned K plus methyl iodide. It would be potassium iodide. So here, in a very artistic display, the data from our first reaction, so when they talked about at the physics colloquium there in 1960, here you see what the parent beam looked like. That little dip there showed how much it was attenuated when crossed by that very short and relatively intense methyl iodide beam. On the tungsten filament, which detected both the product and the atoms, you had a nice bump. On the platinum one that didn't detect the product, you had this, and the difference is plotted here. So this is the kind of picture of the scattering. We had picked methyl iodide specifically because we wanted to use the conservation laws that come from analysis of collisions to tell us that with the energy available from breaking the methyl iodide bond and making the potassium iodide bond, you couldn't get too far away from the direction of the center of mass. We didn't want it to spread all around all possible angles. It might not have had enough intensity. But as it was, this is what corresponded to a monolayer a month, and yet easily detectable, as you see. So, incidentally, not until 10 years later was the puzzle of the differential detection solved. It turns out if you have a sufficiently clean platinum filament, it behaves just like tungsten. And the fact that we didn't have that good a vacuum, it meant that pump oil that was floating around decomposed in the platinum filament, coated it with carbon, and reduced this, really quenched it completely to detect the alkali halide. So that delighted me because Otto Stern had mentioned that in his first experiments, the silver film that he got, in the way I described, was so faint you could barely see it. But if he held it up close, it magically developed. And he said he finally figured out what was going on. He was then an assistant professor. He said he couldn't afford good cigars, so he smoked bad cigars. Bad cigars have a lot of sulfur in them, so when he breathed on the plate, silver reacted with the sulfur. That gives silver iodide, which is, silver sulfur with sulfur, sulfide, which is jet black. It was like developing a film with his breath. So bad breath had an important role in his experiment. A dirty filament had a key role, not just for us, but other young chemists to use this differential detector in the early days of molecular being. So what is the moral here? Well, we're able to study lots of other reactions. I have just a quick sample here. We found some the products sprayed around as if they were from a lawn sprinkler. It showed that they came together and didn't really want to separate in any hurry. They were sort of hugging and kissing and so on, and then would fly apart eventually because energy conservation required it. But many others were very brisk reactions, and you got backward peaking with respect to the direction of the incident beam. This now is a plot measured relative to the center of mass of the collision partners, because there's no chemistry in that. Newton said all you can say about the motion of the center of mass. The relative motion with respect to it is what chemistry, where chemistry comes in. So that, you see, peaks backwards with a certain yield, whereas K plus BR2 gives KBR with huge, much larger yield in the forward direction, and with carbon tet, varying the alkali changes dramatically the shape of the preferred angular distribution. That, when compared with computer simulations using potential energy force functions that represent theoretical estimates of the force fields that may govern the reaction, gave lots of information about it. Here, dominantly repulsive interactions enter. Here, dominantly attractive ones. Here, intermediate. Also, we could later, as I mentioned already, measure the speeds and all, but we'll come to that. Sorry, I don't want to come quite to that yet. So, what I wanted to say here is draw the point of these stories up to now. I say, beyond the importance of good luck, the historical development offers other lessons that I think deserve emphasis. In the early days, when, as you've seen, the chemical scope of this was severely limited, there were three schools of thought. The small group who were excited and optimistic were actually called the lunatic fringe of physical chemistry back then. We were delighted with that title. A much larger group, mostly wise and senior people, were pessimistic because of the intensity problem. They didn't think it had any future. A much larger group are skeptics who quite reasonably felt that although beam studies were finding interesting results for a few very special reactions, after all, they were happening in single collisions, the accessible family was far too small and eccentric to be representative of the broad range of chemical reactions. So I mentioned that, you'll see why. In retrospect, what happened seems characteristic of many new fields designed to be fruitful. The prospects opened up in the early work were greatly amplified because they attracted very able and enterprising people. Graduate students who weren't satisfied doing things that lots of other people had already done in minor variations, they were reckless enough to have the passion to pursue a new line of work that could lead new knowledge. So the same came with postdocs and young faculty and so on. Another thing was it sparked a huge amount of theoretical work. The theorists just had not paid, the chemical theorists, all that much attention to what happens at the molecular level. There were, of course, antecedents to this, but a big surge in that activity, and of course it complemented the experimental work as it developed very much, showing new questions that you ought to try to pursue theoretically. So I wrote here the evangelical fervor. That was something that I would slip in early reviews, and my wife never failed to tease me about it. The lunatic fringe grew rapidly, even though up to 1968, so roughly 8 years, cross-beam studies remained limited just to the family of alkali reactions, this very special one, with halogen-containing molecules. But as I've already illustrated, even for this special family, here you see it, you got unexpected variety, and that was gratifying, even if the reactions were thought to be unrepresentative. What was especially satisfying was because the major thing that happens here is transferring the loose, you could say promiscuous valence electron of the alkali metals, you all know they have one electron outside a closed shell, to a molecule that would like to have, an electrophilic molecule, like to have an electron attached to it. That could be interpreted pretty simply. You had one electron that sort of would enter what we call a molecular orbital on the target molecule. And so as you mapped out dozens of others, these that we're studying in more detail, as you mapped out the variety of these, you could see how the electronic structure of the target molecule governed the dynamics. That's really the holy grail of chemical reaction kinetics. But we, of course, wanted to go beyond the alkali age, as we called it, and there had been a few attempts, and it fostered a very pessimistic view of the prospects. However, in 1967, just when we were ready to move in that direction, an experimental genius joined my lab. Yuan Li. I had met him just before I had left Berkeley. He had grown up in Taiwan. I like to call Yuan the Mozart of chemical physics. Classical musicians especially admire Mozart for his skill in making optimal use of minimal material. Likewise, in scientific experiments that depend heavily on instrumentation, it's vital to make things only as complicated as they need to be, not more so. That's the complimentary statement to Einstein about talking about theory. Otherwise, of course, too many things can go wrong. So, led by Yuan, we were able to construct a new beam apparatus, which we named HOPE. Here it is. I only want you to see that it's a little more complicated than Bertha was. But it's basically the same notion. Here we're crossing a beam of hydrogen atoms. To make those, we had to heat a tungsten tube that would dissociate them and so on. So here we fixed the ovens, which were going to be more complicated because we wanted to make sources of all sorts of reactant molecules. And we rotate the detector, the opposite from Bertha. But the big problem to be solved in making an apparatus that could detect the molecules freshly formed at this intersection. We've seen there are not a lot of them because the beams are dilute enough, so they miss most of the time. Especially you want to velocity select them by time of flight with this little chopper and all. How to differentiate them from the ones that we don't really like anymore. since most of them miss, and molecules being what they are, they bounce off the apparatus somewhere, and those same reactants will get a chance to produce the same product that they produce in single collisions, and that product will, so to speak, ooze through your whole apparatus. So it's key to reduce the pressure in this inner sanctum where you're going to ionize them by electron bombardment. So that was done with a nested pumping system. I would tease Yuan that his Chinese ancestor made toys of that kind. You've seen balls and balls and balls inside. It's a lot like it. And then the second major problem is in this region here, of 10,000 product molecules that arrive, the inefficiency of electron bombardment means only one will get ionized. The other 9,999, if they hit anything, will bounce off and get a chance to get ionized and produce a terrible vacuum background where you don't want it. So how do you solve that? Well, you call on Isaac Newton again. The key thing was to have a symmetric thing where you have a hole on the other side, so if they aren't knocked by an electron and ionized, they just keep going and peacefully leave the apparatus. It's that simple. However, it's really true that other people had made some apparatus that didn't do that. The reason is they were concentrating on the signal and didn't worry what happened after they got to the point of the signal. So the reason I mention this, I think, is of philosophical interest. It's beyond the technical details of making an apparatus like this work. In many cases, I think I think of some political examples, for example. It's more important to figure out how to control and reduce the noise than to focus entirely on the signal. I want to show you what Yuan looked like then, and he was working in constructing this apparatus, which incidentally took 9 months from the first day we started drawing plans and discussing it. 2 first-year graduate students, Pierre LeBreton and Doug McDonald, both of them later became professors at different branches of the University of Illinois. Yuan went on to the University of Chicago and later 25 years at Berkeley. Then he went back to his native Taiwan, where he had a brilliant influence there on their science education as well as science labs all over Asia and mainland China as well. He's now retired. But I've told you how this works, and it enabled many labs to elsewhere to go beyond the alkali age, and lots of interesting things emerged. The next figure illustrates one of the unexpected results that delighted me. I label it the kissing cousins. And of course, here in Spain, where everybody kisses everybody, you may not recognize the term kissing cousins on the other side of the water. It means cousins that are particularly friendly and so forth. You don't just kiss any cousin. It has to be a special cousin. And so it is here. Here are contour maps. That dot in the center represents the center of mass, as I described before. All the chemistry is in motion relative to that. And you can transform the observations you make in the lab to that when you measure the velocity as well as the angle. That's what's done here. And here's H plus Cl2 forming HCl plus Cl. Notice you get sort of a moon shape. What this is a contour map of the intensity of HCl plotted in angle velocity space. So if you go along a ray, you're going out a velocity ray. You climb up contours, go over a peak, and down. So it's more or less that sort of velocity distribution. And you see it doesn't change very much with angle. But it tells you that there's a lot of velocity. The peak velocity here is, again, something essentially doesn't change much with angle. And it's high velocity. And the thing is recoiling backwards with respect to the original direction of the hydrogen atom. So it's what we came to call a rebound reaction. It means there are strong repulsive forces released in the instant of reaction, and that a lot of the energy released goes into translational motion. The rest goes into vibration of the HCl and rotation of the HCl. Now, compare that with this figure here. Amazingly alike. There's potassium reacting with methyl iodide to form Ki. This was thought to be, and is, an example of the electron jump mechanism. Michael Polanyi liked to speculate that should be called the harpoon reaction, with the alkali harpooning the electrophilic target molecule with the electron hauling it in with the Coulomb force of attraction. But that was thought to be a completely different thing than this reaction, where the bonds are covalent in both sides, no ionic and covalent differences there. And hydrogen has only one electron, which hangs on for dear life. So how is it that these have the same distribution? It turns out that the scale is different, but that's accounted for by mass ratios and available energy in making and breaking the old and new bonds. Also, if you compare here with measurements by one of my former students who went on to cross laser beams and study photodissociation, he dissociated chlorine molecule, and a map of looking at one of the chlorines to compare with this, the energy release is amazingly like that. Quantitatively almost the same distribution, same magnitude as in the reaction of the hydrogen atom. So it turned out what we had learned about this one electron kind of thing, we were able, using molecular orbital ideas of the sort Roald Hoffman and Ken Fukuki taught chemists, we could understand very simply why that happened here and why it would be different in other simple molecules. For example, if you shift to bromine and iodine, this distribution changes dramatically and so on. So we call them kissing cousins because the H plus Cl2 was the first reaction John Polanyi studied. It was his prototype favorite case. His method involved observing the infrared emission from the HCl product. It glows faintly in the infrared. And by detecting that, and the distribution, information he gave about the distribution of vibration in the newly formed bond and the rotation of the product, he got information complementary to what you get from a beam experiment, where you find about the translation and the preferred directions of recoil of the product. Because, of course, if you know the translation, you can get the sum from energy conservation, the sum of the vibration plus rotation, or vice versa. If he knows those, he can get a predictor or translational energy release. And so they agreed beautifully and so on. So the kissing cousins refers to the similarity of these. What it means really is we need a different notation for chemical reactions. These make you think, because you're looking at the elements and the individual reactant molecules, about them. But what we need is a notation that shows the nature of the dynamics that comes about because of the intermediate journey of the electron. And I decided not to go into that because I promised to finish in the allotted time. But it's enough for you to know that these basic ideas I mentioned came out. All right, I'll speed up quickly. I have how much more time? Oh my goodness. Okay, I'll speed up even more quickly. Here's a favorite example I included because it's so appealing. When we study H plus ICl, two halogens, we just show the upper is you get distribution equally down below and above, but to show both of them on one plot, this is the HCl form, this is the ICl form. You obviously can form, that should have been HI, anyway, two different products. This should have been HI instead of ICL. Oh, here it is. Sorry. Good. The reaction, right. So you see they're very different shape and all. I used to enjoy asking people to predict which it would go. You see, this releases much more energy. That's what the K means. Much less energy, than the other path that forms HCl. And almost all the chemists would give reasons why it had to be this path. Some sophisticated, some not. But, of course, we knew already that it was probably going to go that way because long ago, Robert Mulliken, in discussing the spectra of ICL, had pointed out that the lower molecular orbitals have sort of in-phase overlap. If you've never seen a molecular orbital before, just think of people handshaking. If they're in phase to shake hands, that's a bonding molecular orbital between them. If they're out of phase, one's going this way and one that way, then there's a node between the original atoms, and that's a repulsive thing. If you count the electrons available, just the valence electrons in the halogen atoms, you have these blue dots for the population of the ICL. We've drawn the chlorine orbital bigger because it has a greater affinity for electrons than the iodine. So these orbitals should involve a more vigorous handshake, if you like, from the chlorine side than the iodine. And this has to go opposite. That's the way you make these things. So it means that these higher orbitals, whether they are empty or full, are both mostly iodine atom orbitals. So you could, from this very simple argument, predict lots of reactions. Because basically, if a reagent came in and wanted to take out an electron or part of an electron, so to speak, it's dealing with the iodine in. If we want to put one in or part of one, it's dealing with iodine in. So it always forms the weaker bond. And many, many reactions fit that pattern. I wanted to show from John Polanyi the kind of data he gets. He also makes contour maps, but this time it's the velocity, the energy distribution in vibration and in rotation. And when he studied H plus ICL, he could only detect the HCl because it turns out anomalous the HI product that is formed has a very weak infrared spectrum, so he couldn't see it. Turns out the HI product is the favorite product, as we saw, and that showed up in his case because even though he's only seeing the HCl, the HCl distribution here is so different in vibration and rotation than it is for H plus Cl2, where you see he saw that from the part that formed only HCl directly. So this gives you a feeling for what the situation was like. Finally, well, it's going to have to be finally pretty shortly, I wanted to say a little about effusive versus supersonic molecular beams. I only mention this because, again, I think it has a broader message. The usual thing that you read in the physics literature is in doing molecular beams, you want to keep the pressure in the source chamber so low that collisions don't occur to distort the flow emerging. So it's called molecular effusion. Chemists, of course, had to get intensity above all, so they would actually cheat a little bit, you know. Actually, chemical engineers had paved the way, John Fenn among them, to work at high pressures, and actually that's a great advantage because then you do have collisions as the molecules come out the orifice, but those collisions are welcome because they organize the beam. This is something all Bostonians understand, but here you're too polite and may not. If you go in Boston to a certain department store, they have a sale Saturday morning, they throw the doors, the crowd rushes in, they collide. They all come to the same velocity, more or less, the same direction. They can't help it. Whereas if they are very excited at the bargain in prospect, they may suffer a extra collision or two, black eye even, and that calms down the vibration and rotation of the molecule also. And that's what happens in the supersonic beam. So what you want to do is let the collisions do the organizing. Same principle that was so fruitful in molecular biology. Let the bugs do the work. Now, this beautiful thing is to introduce Very briefly, notion, I mentioned that those hockey players were all lined up nicely. Actually, the molecules in the beams I've spoken to up to now are tumbling. I'll speak in a moment how we stop that. But it's also true that we can't aim an individual molecule at another one. We have a stream colliding with another one. So there's a statistical probability of hitting them, so to speak, on the nose or the ear or the tummy, right? And that's only statistical. Now, the same is true of the Sultan's archers. This is what the artistic rendition of that crude slide that I drew. So the archers are firing a lot of arrows. I like to think of baseball players, highly paid, throwing pitches to a batter. Those high-paid guys are supposed to be able to throw the pitch where they want it to go, and the batter swings at it in any case. Here, a lot of pitches, so to speak, come at them. The batter can only hit one. What can you do to unravel this? Well, this was thought to be forbidden fruit, forbidden knowledge, no access to it. But I just want to mention, it is possible to undo this because you can act like an umpire and tell where the ball went. The reason you can do that is if you measure the direction and velocity of the exit product and another vector, like the direction of its rotation, which you can do by laser excitation, so it emits fluorescence like a little rotating antenna from a radio station. It tells you its orientation. With those two vectors, you can actually work out and find out where the product was launched from in the dartboard kind of thing in the collision zone. So second, the rotation. Again, that was thought to be something you couldn't stop at ordinary conditions because molecules rotate with peripheral velocity, again, comparable to rifle bullets. Well, in principle, by having a molecule, if it has a so-called dipole moment, an asymmetry in a charge distribution makes one end more positive and one more negative, like HCl would. If it interacts with an external electric field that's strong enough, it'll be want to line up with a favorable orientation with respect to the field. But ordinarily, they rotate so fast, they just speed up when it's favorable and slow down otherwise. So it's a pinwheel, just as you've seen sometimes maybe kids in the playground, their parents feel like making this, and the kid would like it. But if you have a gentle swing, then it goes like a pendulum back and forth. Well, the molecule thing, you can do the same if you slow the rotation beforehand. And we know how to do that. The supersonic beam is the thing that does that from the collisions that cool it down. And so that turned out to be very useful, used in many, many contexts now. And I had in mind to explain a little, which I'm not going to do, about the field of that connects both with Claude's talk tomorrow and Juan's talk yesterday, that involves very slow molecules, so slow, or atoms in your case, that you can trap them in an external field, localize them in space, and then cool them down even further so they move even slower than bugs instead of bullets. And that endows them with dramatic wave properties, overcoming their particle behavior at higher temperature. And that also connects to quantum information theory, as we heard about from Juan, because if we could make enough slow molecules like that and trap enough of them, and if they're polar, you can address them with an external field, and that gets them back to this pendular state. That's what they are. That's the so-called qubits that are proposed in one of the favorite versions of these prospective quantum computers. So now I will just jump to the end. This is the rotor for a device that the Bilbao Museum suggested. This is the authors of that. This is proposed quantum computer with these qubits of different pendular states of rotation. This is their shape, and this is what I think is a very apt poem. I'm delighted we will have a real poet on this podium shortly. This is a poem, a verse exchange between Arnold Sommerfeld and Max Planck. You nobly made arable, that means farmable, a vast new ground wherein I here and there a sprig of flowers found. And Planck wrote back graciously, what you have picked and I have picked, these we will bind together, entwining thus a fair bouquet from gifts we send each other. That's a kind of entanglement. Different than what you spoke about the other day. But it seemed to me this was particularly apt for a celebration of the anniversary of DIPC, because I think it illustrates the spirit of what we do and the fundamental fellowship of science that is one of the most beautiful aspects of it. Thank you. Thank you.